And welcome back to week 5. We're tracking along. We're getting places. Let's look at the current state of the congruent number problem. What do we know? We know that a square-free natural number is congruent if and only if the L function of the associated elliptic curve evaluated at 1 is 0, where one direction relies on a weak version of the Birch and Swinnerton-Dyer conjecture, the BSD conjecture. And this is very profound. It's maybe amongst the most profound steps that we'll take towards the solution to the congruent number problem. But nonetheless, the condition L of En evaluated at 1 being 0 is still not very checkable, mostly because when I say L of En here, I'm referring to the analytic continuation, because as a series, this thing is only defined to the right of the real part equals 3/2. So we have to keep going. We have to find better and better conditions that are equivalent to a square-free natural number being congruent. And to do that, I said we were going to have to jump into the world of modular forms. So let's just do a very fast review of what we talked about along those lines last time. So we're looking at SL2Z, 2x2 integer entried matrices with determinant 1. And we created these fractional linear transformations out of them. And we saw that if we call capital gamma, for example, SL2Z, then that acts on the upper half plane H. So it always takes, it inputs a number Z here. And then this output guy over here, AZ plus B over CZ plus D, that should also end up in H. We looked at some special subgroups of SL2Z, these so-called gamma of n's, where n is a natural number. And what those were just a set of all 2x2 integer matrices with determinant 1 that are congruent to the identity matrix when you reduce the entries mod n. And then I introduced the notion of gamma equivalence. So if I have a point in the upper half plane, and then I look at some other second point in the upper half plane, if that second point happens to just be little gamma of the first point for some little gamma in SL2Z, then we're going to call those 2 points just gamma equivalent. You can get to one from the other by acting on the first one with some element of SL2Z. And then we talked about the fundamental domain for gamma. So it was this kind of region where every point in the upper half plane is gamma equivalent to one of the points in this region F. Okay, and no 2 points in the interior of F were gamma equivalent. And if you recall, that was this kind of strip. Well, one example of a fundamental domain for SL2Z is you take the unit circle in the upper half plane, you look at the lines real part of Z equals plus or minus 1/2. And then if you make the unit circle the lower boundary, and the 2 green lines I just drew, the right and left boundaries, the region enclosed by that boundary plus the boundary itself is actually a fundamental domain for gamma. And we also saw that so no 2 points in the interior are gamma equivalent, but that's not stopping anything on the boundary from being gamma equivalent to something else on the boundary. And we saw that points on the boundary are gamma equivalent sort of if and only if they're right across from each other in some sense. Okay, so the 2 pairs of points that I've just drawn are gamma equivalent. And there are really only 2 matrices governing gamma equivalence within F, and that would be the translation by 1 matrix, the matrix that just sends Z to Z plus 1, and then the matrix that sends Z to negative 1 over Z. And we called those matrices S and T, and we saw that they actually generate gamma bar, which is gamma mod plus or minus the identity matrix as a group. And then we looked at H mod gamma, which is really just F with all the gamma equivalent points identified. So it's like a funnel type shape. It's not really a funnel, but something like that. And we kind of drew parallels between this situation and the elliptic curve situation. Namely, we took lattices in the elliptic curve, in our elliptic curve studies, and we made tori out of them. And then we made those kind of biholomorphic and group isomorphic to complex projective elliptic curves, right? To get a projective elliptic curve, though, you have to take an affine elliptic curve, really, and add a point at infinity. So we're motivated here to somehow add a point at infinity to our setup. The problem is, and it's not really a problem, but you can't really just add the point at infinity to this region F, because then if you act on it by members of SL2Z, you end up with rational numbers, right? And the rational numbers are currently not in the upper half plane. So what we have to do is not only add a point at infinity to the upper half plane, but also the set of all rationals. And those points are called cusps. And as a matter of fact, when I say cusp of the upper half plane, there's really only one cusp, because when I say cusp, what I mean is a gamma equivalence class of cusps. And you can show that the orbit there's only one orbit when you act on the set of all points that we added with gamma. So you can always get from one rational to any other rational, or to infinity, or from infinity to any rational by acting on that point with some member of gamma. So there's really only one cusp, and we call it the cusp at infinity for gamma. But there's nothing stopping you from taking subgroups of gamma and asking, what's the deal with the cusps there? Because in general, it doesn't have to be the case that a subgroup of gamma permutes all the cusps transitively. There might be more than one orbit, so there might be more than one cusp then by definition. But the big group gamma only has this one cusp, and we just call it the cusp at infinity. And I ended last time by discussing this kind of elementary fact from complex analysis. If I take H union infinity, so the upper half plane with the point at infinity, I can map that to the open unit disk with the following map. I can send Z in the upper half plane to Q, and Q is going to be, from now on, we're going to refer to Q as, we're going to refer to e to the 2 pi iz as this variable Q. And then you can send infinity to the origin. Okay, and this is it's easy to check. This is a continuous map on H union infinity. And so what that means is what's going on near infinity, so to speak, in the upper half plane is really the same as what's going on near zero in the open unit disk under this map. And that's good, because that allows us to very nicely define what we mean by like a meromorphic function on the upper half plane at infinity. So if I take a meromorphic function f on H, so that it has period 1, the reason for period 1 will become apparent in a second. I'm going to call that meromorphic at infinity if I can express f as a power series in this variable Q under this map here, like this. So as a series over the integers of some coefficients an times q to the n. And we'll say we're meromorphic at infinity if there's at most finitely many negative index terms, which is exactly what you'd expect from the definition of a meromorphic function, right? Just think of Laurent series, for example. You only want finitely many negative index terms. If you have that under this correspondence here, then you're going to be called meromorphic at infinity. And you can see why here we want, period 1. It's because of the definition of this variable Q. We have this e to the 2 pi iz, which is periodic in period 1. So that's what it means for a meromorphic function of period 1 on the upper half plane to be meromorphic at infinity. Transport everything over to the disk. Look at your power series expression for f, and if it's got only finitely many negative terms, you're meromorphic at infinity. Okay, we're holomorphic at infinity if you have no negative index terms, which is again exactly what you would expect. That's kind of the typical Laurent series definition of holomorphicity. You only have, if you want to be holomorphic at infinity, you better not have any, a sub -1, a sub -2, a sub -3, and so on. And then we're going to say f vanishes at infinity if it's holomorphic at infinity, and the zero coefficient is 0. Which is exactly what you would expect, right? Because vanishing at infinity for f on the upper half plane is really the same thing as f vanishing at 0 here in the variable Q, because you've sort of sent infinity to 0 under this map. And when does that happen? When will it happen that when you plug Q equals 0, so to speak, into the series and you end up with 0? Well, assuming you're holomorphic, the only way that's going to happen is if the 0 term is 0. Okay. And one last little definition before we go on and actually talk about what modular forms are today. We're going to let F bar be the set H mod gamma, which is F, this region here, with gamma equivalent points identified, so it's the funnel-y thing, but then with the point at infinity added. Okay, so it's like the funnel shape thing with one more point at infinity added. We're going to call that F bar. And by the discussion we just had and the discussion we had last time, what are the points of F bar? They're really just gamma equivalence classes of points in H bar, excuse me. Okay, so now that we understand this basic framework, I can actually define for you what modular forms are. But I will start by defining modular functions first. So from now on, we're going to let gamma be this 2x2 matrix ABCD. It's going to live in SL2Z, which is gamma. If F is meromorphic on the upper half plane, and there exists some integer k such that F of gamma acting on Z is CZ plus D to the K times F of Z, where C and D are these bottom two entries of the matrix, and K is the integer over here. For all gamma and big gamma, and in addition, F is not only meromorphic on H, but meromorphic at infinity, then we're going to say F is a modular function of weight K. So this K here is the weight of the modular function. And it doesn't really make sense to say modular function of weight K. I have to tell you with respect to which subgroup of gamma is this modular. And of course, because we're requiring this to be true for all gamma and big gamma, this would be a modular, if you satisfy these conditions, you would be a modular function of weight K for the full group gamma. Okay. And we'll talk about modular functions and modular forms for subgroups of gamma later. The definition is slightly different, but so here's what it is. If you've been wondering what a modular function is, here's what it is. It's a function, it's a meromorphic function on H bar, or on H union infinity, that's got this nice kind of symmetric property about it, where if you want to act on your input with some matrix in SL2Z and then take the function at that value, really you can just take the function value at Z and then sort of scale the result by this linear function that only involves C and D in the matrix. And so what's a modular form? Well, it's a modular function that's also holomorphic at infinity, okay, which we just defined above. So if you're meromorphic on H and holomorphic at infinity, and you've got this nice scaling, I don't even know what to call this. I usually just call this the modularity condition. But if you have this nice modularity condition for all gamma and SL2Z, then you're a modular form of weight K. And lastly, if this happens to vanish at infinity, if your function, in addition to all of the above, also vanishes at infinity, then we're going to call F a cusp form of weight K for gamma. So you've got modular functions, which aren't particularly interesting because they're not holomorphic at infinity. When you require that they're holomorphic at infinity, then things start getting good and nice for you. So you end up with modular forms. But then if the function actually vanishes at infinity, you have a cusp form. So some notation, the modular forms of weight K for gamma will be denoted by M sub K of gamma. And the cusp forms of weight K for gamma will be denoted by S sub K of gamma, because S for some reason means cusp. I don't know. But the other thing is this definition, it relies heavily on this series right here. It relies heavily on whether or not you have finitely many negative index terms here, no negative index terms, or a vanishing zero term, because those criteria are exactly the definitions for meromorphic at infinity, holomorphic at infinity, and vanishes at infinity. So because this series is such a crucial, part of this discussion, we're going to give it a name. If I take a modular form or modular function, whatever you want, F, and I write it like this, we're going to call this series its Q expansion, the Q expansion of F. So you transport everything over the disk, you make this little power series about 0, and you've got your Q expansion for F. So we can now that we have all the definitions in front of us, we can go off to the races right away. So first of all, for example, I'll give you 4 exercises, and they're all easy. The first thing is there's no non-zero modular weight. There's no non-zero modular functions of weight k for k odd, which might surprise you, but when you look at what's actually going on here, you'll see that this is trivial. So from now on, k will be an even integer, not just any integer. Second, it actually turns out that a function which is meromorphic on H, union infinity, is a modular function if and only if this modularity condition is, it doesn't actually have to be satisfied for all gamma in big gamma. It only has to be satisfied for the translation by 1 and the negative inversion matrix, which shouldn't surprise you at all, right? Because we know that those matrices generate the group gamma bar. Okay, and we will not really heavily use this fact, but it's still interesting. The third thing is all 3 of these spaces, and by all 3 of these spaces, I mean modular functions, modular forms, and cusp forms. They're all complex vector spaces. So in particular, they're closed under scalar multiplication and addition. And modular functions of weight 0 are actually a field. Again, this is very easy to check. And what happens if you, I don't know why I'm leaving this as a question because this is sort of important, but if you multiply 2 modular functions, one of weight k1 and one of weight k2 together, you're going to get a new modular function of weight k1 plus k2. And I'll let you figure out why that is and what happens when you divide. When you divide, you're going to subtract. And if that function actually happens to be a form, then the new form that you get post multiplication will again be a form. And if the starting guy happened to be a cusp form, then what you will get after multiplication is also a cusp form. Okay. And as another exercise, a final exercise, find a nice, succinct, easy way of describing k equals 0 and k equals 2, weight k equals 0 and k equals 2 modular forms. They're not particularly interesting. And remember, k is even from now on, so that's why I excluded 1 here. Okay, so let's look at some examples. I mean, this is great. This is a nice, cute little setup, but are there any actual examples of these things? Yes. So a very important example of a modular form is the following. We didn't derive the actual, well, wait a minute. Did we actually talk about, we may have actually brought this up explicitly. Let me just quickly check. Back when we were, no. Actually, okay, so we kind of did. Back when we were talking about the Weierstrass normal form of an elliptic curve, I told you that it's, let's see, where is it? I lost it somehow. Where did it go? Wait a minute, I just saw it a second ago. Am I not far enough up? I just had it and then it flew away on me. Oh, here, right here. So I told you that actually this was the expression for the Weierstrass normal form of an elliptic curve. And what were these G2Ls and G3Ls? We had expressions for them. G2L was 60 times the sum over all non-zero points of the lattice of 1 over L to the 4th. But what do points in the lattice look like? Well, if you rotate any complex lattice, we'll talk about this later, you can assume that the 2 generating vectors are 1 and then some z. Okay. And so if you assume that, then what do points of the lattice look like? They look like integer multiple linear combinations of 1 and z. So they look like n plus mz, right? And so this sum here would actually end up looking like, forget the 60 for a second, it would look like sum of 1 over n plus mz to the 4th, where the sum is over, m and n, assuming n and m aren't both 0. And the same thing happens here. We would end up with a sum of 1 over n plus mz to the 6th. for this G3L. So what I'm trying to say is, if you go back now to modular forms, we've encountered this function before. The sum over integers mn of 1 over mz plus n to the k, where k is bigger than or equal to 4 and even. We've encountered it twice, once when k was 4 and once when k was 6. And both of these expressions times some scalars, 60 and 140 respectively. Both of these popped up when we were discussing the Weierstrass normal form of an elliptic curve. Well, this series has a name, and it's called the Eisenstein series of weight k. And here z is an h, okay? And so this guy popped up when we were talking about complex elliptic curves. And so I'm going to give you right now an immediate connection between modular forms and elliptic curves in the form of the following proposition. It turns out GK, the weight k Eisenstein series, is a modular form of weight k for gamma. And as a matter of fact, we know its Q expansion completely. Its Q expansion is 2 times the Riemann zeta function evaluated at k times this whole quantity here. The first coefficient, the 0 coefficient, is just 1, minus 2k over b sub k, where b sub k are the Bernoulli numbers, times the sum of this sigma sub k minus 1 of n, q to the n. And sigma sub k of n is a function that pops up a lot when you're discussing this type of thing. All it is the sum of all the divisors of n raised to the k power. So this would be sum of all the over all the divisors of n, of the divisors raised to the k minus 1 power. Okay. And what you often want to do with modular forms is normalize them so that their leading term is 1. If you distribute this 2 zeta of k here, though, you're going to see that your leading term is 2 zeta of k. So this is not a normalized modular form, but I can easily make one, right? I can just take g sub k and I can divide by 2 zeta of k. And when I do that, I produce this function e sub k of z, and that's called the normalized Eisenstein series of weight k, because its leading coefficient, or its leading term rather, is now 1. Okay. And as an exercise, you can actually show that e sub k of z looks a lot like g sub k of z. It's the same summand, 1 over mz plus n to the k, but now the sum is over just pairs of co-prime integers m and n, and then times a 1/2 out front. So that's a nice little thing to try if you want to show that. Okay, so what are some other examples of modular forms? We've got the Eisenstein series, and more importantly, the normalized Eisenstein series, which show up when discussing complex elliptic curves. Well, there's a notion of a discriminant of a curve, which the discriminant of a curve is really this function that it kind of vanishes if and only if your curve has distinct root, has a repeated root. In other words, it's non-vanishing exactly when this cubic here, in this case, has distinct roots, i.e. whenever this curve is elliptic. Okay, you probably learned about discriminants, I don't know, at some point during your undergraduate, but you can actually view discriminants very importantly through the lens of modular forms in the following way. So again, let me write down now kind of formally what I was talking about above. If I take some lattice, right, in the upper half plane, let's say, so let's draw one little fundamental parallelogram of a lattice. And let's say, for example, the lattice, at least initially, is generated by these two vectors here. Okay. Then my fundamental parallelogram would look something like this, and my lattice would be pretty ugly because it doesn't line up nicely with the real axis. But if you just suitably rotate any lattice in the upper half plane, you don't disturb anything up to conformal equivalence. And so you can always assume that whatever lattice you're working with in the upper half plane is generated by, let's say, the vector 1, which was this vector here, and then some other z in the upper half plane. Just a simple rotation will do that for you. And now you've produced a much better, kind of nicer to handle and and homogeneous lattice in the sense that every lattice can be kind of thought of this way. So what we're going to do is we're going to take a lattice in the upper half plane. We're going to suitably rotate it so that it's in this form from now on. And when we do that, the result will be what we'll call L sub z. And what that will be is the set of all integer linear combinations n plus mz, which is really what? It's just the lattice itself, right? Because this is just all combinations of the generators 1 and z over the integers, okay, for z in the upper half plane. And then you know that corresponding to each one of these lattices, right, you've got some elliptic curve that pops out. The Weierstrass normal form we talked about, using the Weierstrass phi function. We talked about that a couple weeks ago. So what that allows you to do then is think of the discriminant as a function of z in the upper half plane. Because for every z in the upper half plane, you get exactly one of these lattices. For every one of these lattices, you get a unique complex elliptic curve. And then every one of those unique complex elliptic curves has a discriminant, delta. So we can think of delta as a function delta of z. And as an exercise, this actually isn't hard to show, although I'm not sure that I quite gave you all the details you might need, but if you'd like, view this as a proposition instead. It turns out the discriminant as a function of z is 2 pi to the 12th over 1728 times some modular forms. E sub 4, so the weight 4 normalized Eisenstein series cubed, minus the weight 6 normalized Eisenstein series squared. And because we know that when we multiply modular forms together, we end up with other modular forms. So this would be a weight 12 modular form, because it's a weight 4 plus 4 plus 4 modular form. This would also be a weight 12 modular form. But then we also know that the spaces of modular forms are complex vector spaces. So when I subtract these, I'm going to get another weight 12 modular form. It actually turns out that delta is not only equal to this, so it's not only a weight 12 modular form, it's actually a weight 12 cusp form, which is easy to see. What is much harder to see is that if you kind of kill off this 2 pi to the 12th by multiplying by 2 pi to the negative 12th, the resulting modular form actually has integer coefficients and it's normalized, okay? So that is not very easy to show. In fact, even showing that the coefficients are rational is a little bit, it's not that hard. It's just a little bit of power series manipulation. But so that's nice to know. So the discriminant of an elliptic curve is actually a modular form when thought of as a function on lattices, basically. Which, by the way, is yet another connection between elliptic curves and modular forms. It's like their discriminants of elliptic curves are suddenly modular forms, okay? As a small remark, you can show there's a very small problem for weight 2 in the sense that E sub 2, then the weight 2 normalized Eisenstein series is actually not modular. I'm not going to get into this, but it turns out it doesn't even matter. You can very slightly and naturally modify it so that it is a modular form. But if you just define it like this, like kind of just, you just set k equal to 2 here, that's actually not a modular form. Okay, so now we're going to see a very remarkable proposition that we're going to use to kind of dig up a bunch of information on the spaces of modular forms and cusp forms. Here's the governing proposition. So we're going to let f be a non-zero modular function of weight k for gamma. We're going to let p be some point in the upper half plane. And we're going to denote by v sub p of f the order of the 0 or the negative of the order of the pole for f at p. So if f has a, you know, an order 2 pole at, I don't know, p equals I, then v sub I of f would be -2. If f had a 0 of order 3 at I, then v sub I of f would be 3, okay? And we're going to let v sub infinity of f be the index of the first non-vanishing term of the Q expansion for f, which is exactly what it should be. That's kind of measuring like how meromorphic is f in some sense. And then we're going to let omega be the lower left corner of our fundamental domain F. Here's my fundamental domain. Boom, boom. Here's omega. And it turns out the following is true. V sub infinity of F plus 1/2 V sub I of F, and I am referring to the point I. Okay. Plus 1/3 V sub omega of F, plus the sum over all the rest of the V piece of F's, where P kind of lies in the fundamental domain up to gamma equivalence, but it's not I or W because we've already taken care of those. If you add up all those kind of orders and you scale them appropriately, you end up with K over 12, where K is the weight of the modular function, which is incredible. This is basically a big Cauchy's formula residue theorem computation. And furthermore, and this is easier to see, all of these V sub P's here, they're all unchanged actually if you replace P by gamma of P for any matrix gamma in SL2Z, okay? And if you play around with this and choose different K values, you end up with some remarkable consequences. You can like describe entire spaces of modular forms just with this one equation. And here are some of the things that you get. So we're gonna let K be even as usual. Then we get 5, actually, we get at least 5 things right away. The only weight 0 modular forms for gamma are the complex constants. That's the first thing. Part B, if K is negative or 2, there's only one weight K modular form and it's 0. Okay, which is huge. That means we're kind of justified up here when we talk about like, oh, here's the Eisenstein series of weight K, but K is bigger than or equal to 4 and even. And then also down here, E sub 2 is not modular. Like problems like that are kind of illuminated by this proposition here. It's kind of like, it's understandable now why we would run into such issues. If K is 4, 6, 8, 10, or 14, you notice I skipped 12, then the dimension as a vector space of the modular forms of weight K is 1, and it's generated by, as a vector space, by the normalized Eisenstein series of weight K. So the E sub K's are even more important than we thought they were. They weren't just tied to the elliptic curves. They're also like the generating function for the entire space of modular forms. If K is less than 12 or 14, then the space of cusp forms of weight K is 0. Okay, so again, we skip over 12 here. What's the deal with S12? Well, you remember from above, the discriminant was a weight 12 cusp form, right? It turns out the space of weight 12 cusp forms for gamma is just generated by the discriminant as a C vector space. It's just C times delta. Okay. And if K is bigger than 14, so we kind of understand what happens less than 12, and at 14. What about bigger than 14? If you're bigger than 14, then actually the space of cusp forms is just delta, the discriminant function, times weight K minus 12, the space of weight K minus 12 modular forms. So everything in the weight 12 case is governed by the discriminant. And everything in the weight 4, 6, 8, 10, 14 situation is governed by like these normalized Eisenstein series. And you notice there are some there are some spaces, some isolated spaces we left out and we can't get any information on from this. What's a more general fact about these spaces? Well, it turns out that for any K bigger than 2, the space of weight K modular forms is just the space of weight K cusp forms direct sum with C times EK, where EK is the normalized Eisenstein series. So it's like the cusp forms and then multiples of EK and like nothing or formal sums of those or sums of those and nothing else, right? Another thing you can get out of this discussion up here is the following fact. any weight k modular form for gamma must be of this form. It has to be some, complex number, c sub I j, times the weight 4 normalized Eisenstein series to the I power, times the weight 6 normalized Eisenstein series to a power j. And what are the conditions on this I and j? You just need 4i plus 6j to be this k, to be your weight. So any modular form of weight k looks like this, and conversely, of course, all of these are also weight k modular forms. Okay. So that's quite a lot of information just right out the gate without much investment. There is a very special modular function of weight 0, though, that you should be aware of, and it's the so-called j-invariant. And what it is it's 1728, that number 1728 shows up again, times e sub 4 cubed, so that's a weight 12 modular form, over e sub 4 cubed again, so that's weight 12, minus e sub 6 squared, which is again weight 12. So we have a weight 12 divided by a weight 12, that's a weight 0. So we've got a weight 0 modular function here. And the 1728 is for normalization reasons. It also incidentally helps out with some of the characteristic problems that might occur if you're doing all of this over, I don't know, if you're trying to set this all up in characteristic P or something. But so this is normalized and it's a weight 0 modular function. And what is the importance of this weight 0 modular function? Well, the next proposition is huge. So proposition 11. The j-invariant gives a bijection between f bar, which you'll remember is the fundamental domain with sides identified. So you get the funnely thing, and then with the point at infinity added, and the Riemann sphere, so the complex sphere. So, and furthermore, we understand exactly sort of what prevents J from being a modular form. It actually has a simple pole with residue 1 at infinity, and that's its only pole, but it's holomorphic everywhere else on H. And this should remind you of something, right? Well, actually, let me talk about that in a moment. Let me get through proposition 12. So proposition 11 just says the j-invariant gives you a bijection between your fundamental domain with infinity added and sides identified and a sphere, a complex sphere. And not only that, but it turns out all modular functions of weight 0 for gamma are just rational functions of J. If you take these two propositions together, they should remind you of previous discussions that we had. Remember back in the complex curve studies that we did? What did we see? We saw every complex torus was biholomorphic and group isomorphic to a projective complex elliptic curve. And here, what are we seeing? We're kind of seeing like quote unquote projectivized fundamental domains for gamma are biholomorphic to complex spheres. So there's another parallel here between the elliptic curve situation and the modular form situation. There's another tie-in. Not only that, but remember when we were studying elliptic functions, what did we discover? We discovered that the subfield of even elliptic functions was generated by the Weierstrass V function, which I wrote right here. But proposition 12 says the weight 0 modular functions for gamma are the rational functions of J. So the even elliptic functions are rational functions of the Weierstrass V function. And the weight 0 modular functions are rational functions of the j-invariant. So again, there's all these little parallels that pop up between elliptic curves and modular forms, and you got to pay attention to all of them because you never know when you're going to need them later. And so there's all that. We're now in position to actually fill in a gap from earlier in the lecture. So earlier in the series of talks, I showed you every complex lattice in the upper half plane admits a unique projective, or is not admits, it's biholomorphic and group isomorphic, even isomorphic as Riemann spheres, or as Riemann surfaces rather, to a complex elliptic curve that's projective. But we were not able to show that if I give you a complex elliptic curve that's projectivized, that comes from some complex lattice. So in other words, we weren't able to really show that there was a one-to-one correspondence between complex tori and projective complex elliptic curves. And we're now in a situation, thanks to modular forms, where we're able to do that. So theorem. So we already know every complex torus is biholomorphic and group isomorphic to a complex projectivized elliptic curve. Great. We now can show the converse. Every complex elliptic curve has a Weierstrass normal form and is the elliptic curve that naturally arises from some lattice in H. And I'm actually going to sketch the proof of that. I'm not going to do every detail, but first of all, the fact that every such elliptic curve has a Weierstrass normal form is just a matter of doing a bunch of linear changes of coordinates. Okay, so I'm not going to go through that. You can get every elliptic curve, you can get every complex elliptic curve into this form. Y squared equals 4x cubed minus ax minus b. I think Silverman's books cover this. So if you want to see that, you can check that. And we also know that the smoothness condition will happen exactly when? It will happen exactly when the roots of this cubic are distinct. We've talked about this already. But what does it mean for the roots of this cubic to be distinct? It means the discriminant of this elliptic curve is non-zero. Okay, because the classical definition of the discriminant is it's the product of the differences of the roots squared. So that will be non-zero if and only if the roots are distinct. If you take the cubic formula and combine it with Vietta's formulas and you do a bunch of computations, you can actually pretty easily compute the discriminant of this curve. It ends up being a cubed minus 27b squared up to some maybe scalar multiple, non-zero scalar multiple, depending on how you want to define things. And so, but what was the Weierstrass normal form for an elliptic curve admitted by a complex lattice? Well, it was this. It was y squared equals 4x cubed minus this g2 of L times x minus g3 of L. So in light of all this, what do we need to show? We need to show there exists a lattice L such that g2 of L is this A and such that g3 of L is this B. That's all we really need to show. Okay. So what we'll do is we'll write a stereotypical lattice as, you know, the set of all nw1 plus mw2, where n and m are integers as usual. And w1 and w2 will be the vectors that sort of generate the lattice. Then, as we've already talked about, by suitably rotating the lattice, we can make sure it's actually in this form here, this L sub z form. So it's generated by 1 and z for some z in the upper half plane. Okay, so we're going to call that new kind of rotation L sub z. In fact, the thing that you scale the lattice by to get L sub z is just W2, right? Now, when we talked about this earlier today, actually, when we built the Weierstrass form of the elliptic curve admitted by a lattice, we came up with the following expressions for G2 and G3. G2 was 60 times the sum over all the non-zero lattice points of L to the negative fourth. And G3 was 140 times the sum over the same lattice points of L to the negative sixth. It's then very easy to check, I mean, there's nothing to it, that if you take G2 of lambda times LZ, so scale all the members of your lattice by lambda, then you're just going to get lambda to the negative fourth times G2 of LZ, so LZ unscaled. And then similarly, G3 evaluated at the lattice lambda of LZ, lambda times LZ, is going to be lambda to the negative 6 times G3 of just LZ with no scaling by lambda. It's also not hard to check. It's actually just from the definitions, actually, that G2 of LZ is just 4 pi to the fourth over 3 times the normalized Eisenstein series of weight 4. And similarly, G3 evaluated at the lattice LZ is 8 pi to the sixth over 27 times the weight 6 normalized Eisenstein series. You could do all these computations easily yourself. Once you realize all this, you can restate the theorem as follows. There must exist a lambda and a z such that the weight for normalized Eisenstein series is lambda to the fourth times 3 over 4 pi to the fourth a, and E sub 6 is lambda to the sixth times 27b over 8 pi to the sixth. That just involves rearranging these equations, using these two facts, and using the fact that the discriminant is non-vanishing for an elliptic curve, okay? And you can clean this up a little bit. You can call this 3a over 4 pi to the fourth, you can just call that little a. And then you can call 27b over 8 pi to the sixth, you can just call that little b. And then what you have, which is just completely trivial, is the discriminant of the given elliptic curve, the one that we want to know, does it come from a lattice or not? That discriminant is non-zero if and only if a cubed is not equal to 27b squared, which just comes from here. This will be non-zero if and only if a cubed is not 27b squared. But in the language of little a and little b, that will happen if and only if little a cubed is not equal to little b squared, which is very clean and very simple. So we know this now. We know little a cubed is not equal to little b squared because we have an elliptic curve and the discriminant cannot be zero because the roots are distinct. Okay, so here's how the rest of the proof proceeds. Let's suppose you're able to locate a z in the upper half plane such that this ratio equation is satisfied. E sub 6 squared over e to the fourth cubed is b squared over a cubed. Okay. And by the way, it's occurring to me now, what would happen if a is 0? I mean, a is technically allowed to be 0 here, right? There's no reason a can't be 0. I'm not sure what happens in that case, actually, but it's probably a little niche case that's not that important. I'll think about it later. But so suppose you're able to find a z where this happens. Okay. Now what you're going to do is you're going to choose lambda such that e sub 4 evaluated at that z is just lambda to the fourth a. You can always find a complex scalar where that happens. Okay. Now, once you've chosen lambda, here's what happens. Solve for e sub 6 squared here. You get e sub 6 squared is what? B squared times e sub 4 cubed over a cubed. But e sub 4 is z is what? It's lambda to the fourth a. So what you're going to get is lambda to the 12th a cubed over a cubed b squared, and the a cubeds cancel. So you're just left with lambda squared b squared. And so what does that tell you? That tells you if you're able to find such a z where this happens, then e sub 6 must be plus or minus the square root of this, which is plus or minus lambda to the sixth b. And it's easy to check that if it's plus, okay, then lambda, this should say does, then lambda actually does the trick, and you have found the lambda and the z that you were after here. And if it's minus, then if you replace lambda by I lambda, then z comma I lambda are exactly what you're looking for up here, satisfying these conditions. So great. The only problem with this proof is, besides the little if a equals 0 thing, which I need to think about, but the only problem is, how do you know this z exists such that this ratio, these ratios are equal to each other? I will leave that as an exercise, and my hint to you is use all the properties of the j-invariant that you know. The j-invariant is the key to showing this z exists, and if you use its properties correctly, the fact that this z exists will pop out right away. So great. So we have shown every complex elliptic curve comes from some complex lattice. And so there's a one-to-one correspondence between these two objects, and modular forms were really kind of the key to the proof, right? These normalized Eisenstein series. Okay, to end this little section here, I want to leave you with two facts. that you should be aware of and that we may call upon in the future, although we will not be like heavily reliant on these, but they're just good to know. There's this important function in number theory and in the study of modular forms called the Dedicand eta function. It's a function on the upper half plane, and here's what it is. Eta of z is defined to be e to the 2 pi I z over 24 times the infinite product of over n of 1 minus e to the 2 pi I n z. So what you want to be aware of is this guy actually has a functional equation. And we will use this again later. Okay, not heavily, but we will see it again later. This guy has a functional equation, and it's given by this. Eta evaluated at -1 over z, it turns out, is just the square root of z over I times eta evaluated at z. And which square root? Just the typical non-negative real part, branch of the square root. Okay, so that's something that we'll need later. This special function will come up again. And then, and by the way, I could have also written this in terms of the variable q, right? Because e to the 2 pi I z is q. So I could have written this as q to the 1/24th times the infinite product of 1 minus q to the n, if I wanted. And as another very interesting proposition, remember the discriminant from above? Well, we found some nice facts out above about 2 pi to the -12th times the discriminant. It was a modular form it was a cusp form of weight 12 for gamma, and it had integer coefficients and it was normalized. It turns out we actually know much more than that about the discriminant. It's actually got this q product. It turns out it's q times the product over n, 1 minus q to the n to the 24th power. Okay. And if you expand all this out, of course, you get an infinite sum, right? Starting at 1. And it's kind of a q expansion sum. So it has coefficients that depend on n, and those coefficients are usually called tau of n. And tau of n as a function is called the Ramanujan function of n. And I will, as we progress, further along through this, I will give you more information about tau sub n. But this, you should, look up this Ramanujan function. There's some interesting properties about it that you can show. And both of these facts are crucial to the study of modular forms in general. If I don't ever explicitly mention them again, that doesn't mean they weren't used like in the proofs of things that we're going to talk about. But I do believe that at least this comes up, or at least this comes up again explicitly later in the talk. Okay, so next time the aim is can we play this same game for subgroups of gamma? What if I don't want modular forms for the whole big SL2Z? Is there a way to naturally and correctly define modular forms for subgroups of gamma, namely the congruent subgroups maybe that we've been talking about, or gamma sub 0 or gamma sub 1? Do those have modular forms, and what does that definition look like? So I think that ends, boy, time sure flew there, for me anyway. So I think I'll stop here. And if there are any questions, I'm happy to take them, either push to talk or type them in chat, whatever you want to do.